All right, hi there, everybody. This will be a topic that I hope is very familiar to you, topic of continuity and what is required for things to be continuous, wanting to make sure we are building on good, strong definitions. So we'll talk about how do we define continuity, the different types of discontinuities there are, what we can and can't do with continuous functions, and then we'll finish up with the IVT. So just as a review visually, continuity can be described as something that can be sketched without lifting up your pencil. It's one continuous motion. And so if you're looking, it's, something like this, where we don't have any breaks, okay, then we can say that that is a continuous function. Passes the VLT and has one smooth continuous motion. When we define continuity, then we use a mathematical definition of that. So to define the continuity, we have to look at what's happening as we approach the value from the left. What happens when we approach the value from the right? Those must be equal to the same value of L. And then also what distinguishes it, that's the limit part. And then when we say the function value must be a closed hole at L as well. So all three of those things must be equal to L, and then we have something that is continuous. When something's discontinuous, you have a couple types. You have removable. Removable is where you have one single point removed like that. It usually comes from factors that are reduced, so reducible factors. So if you have the same factor in the numerator and the denominator and it reduces away, the result in the graph is that you would have a hole at that point. We've got jump, which is going to be a gap. Sometimes we call that a gap discontinuity as well. We have an infinite. An infinite is when you come up against an asymptote and that asymptote provides a wall that you can't go on that across that boundary. So and then we have oscillating, which is where a graph is fluctuating so fast between positive and negative values that you can't establish continuity. There is no continuous pattern of being continuously positive or continuously negative. It's always changing back and forth. So there's some of the visual ones that we're looking at. This graph, the first graph is continuous. The second graph is a removable. You can kind of see if I zoom in on that is a missing point. The third one is also removable, and it's also been replaced elsewhere, so we have a replacement value. We have our jump discontinuity. We have a infinite or asymptotic discontinuity. And you can tell that there is a asymptote running here down the y-axis. And then we have our oscillating discontinuity. Graph of sine of 1 over x is a famous example of that, where and the farther you zoom in, the more and more positive and negative values you see. So if you're asked to identify points of discontinuity, clearly you can see that there is an infinite discontinuity here with the asymptote. If you have to prove it, so to prove it, you need to tell me what's happening as you approach the asymptote from both sides. So if you approach it from the left, the graph shows us that we're heading towards positive infinity. If we approach it from the right, then the graph also shows us that we're approaching positive infinity. But no two values of infinity are equal, so that is considered a discontinuity because the left and the right hand values of the limit are not the same. All right, so when it is continuous, it's continuous on its interval. And so an interval can be established. Look at, this interval of a graph, and maybe the jump discontinuity is somewhere else outside of the interval. Then you can say it is continuous within the interval as long as the jump is maybe on the left side or the right side of the interval. So you are allowed to shorten your interval and not look at all real numbers. Okay, this graph has again an asymptote at -2, so we have an infinite asymptotic discontinuity going on. But -2 is also not included in the domain. So if you're asked about all real numbers, this is discontinuous on all real numbers, but it is continuous on the domain because the domain will exclude -2. So you can kind of get around some things. That's kind of the difference between some of the true false or the multiple choice questions. Be careful, are they asking for the domain of all real numbers, or are they asking for a different domain? And if so, on the domain they're given, is it continuous at least on those values? When things are continuous, you can do lots with them. If two functions are continuous, you can add them, subtract them, multiply them. You can do what's called scalar multiplication, where you multiply by a constant. And you can divide as long as the denominator is never equal to 0 at any given time. You could also compose functions. So this is one notation of composing. You also can do g of f of x. So as long as both functions are continuous, you're allowed to do that. You can also compose the opposite direction, and you are allowed to compose that way, f of g of x. So both of those are allowed if f and g are both continuous in the first place. All right, the IVT. This was a theorem we worked on last year, and it really, really helps. The word intermediate, another synonym for that is to be in between. So sometimes it's the in-betweenness theorem. So we want to know what is going on in between values. That if you are given an interval and it's continuous, all values in between are considered. And so f of c exists. You can guarantee that everything will exist between f of a and f of b. So we say if f is continuous on a to b, and it's a closed interval. Okay, you can see the brackets here that we do include the endpoints. So if f is continuous on those intervals, then every value between f of a and f of b also exists. And so that is a guarantee of the existence of values between them. We use this a lot to show the existence of a 0. So if something is a negative value, if one of the endpoints is a negative value, so we'll consider that as an endpoint. And if the other endpoint is a positive value, then 0 has to be a value of existence between those two things. That's where the intermediate value theorem is most powerful. But continuity is required. If continuity isn't there, you can't use this intermediate value theorem. So you can see graphically here, if we've got endpoint A going on here, and we've got endpoint B, then we are guaranteed between them, if you could draw a straight line between them, that all of those values will exist at some point. It doesn't have to be a straight line. It can be loopy, like the one we have here with different concavities to it. But every value between, there's no point that's left out. Every value will be covered at least once. Another way you can think of it is it's going to be connected. It's going to be unbroken. There are no brokenness. Will not have any jumps. Will not have any separate branches like a hyperbola. A hyperbola does not fall under the category of IVT because a hyperbola is broken by an asymptote into two pieces. All right, so let's take a look at a sample problem that would be pulled from like an FRQ or an AP question. So we're given the key that we're working with a continuous function. The function is g of x. The question is asking us about the interval from 0 to 2. So we want to look at what the endpoints are of the interval from 0 to 2. So our endpoints would be what is g of 0, and that endpoint is 7. And the other endpoint would be what g of 2 is, and that's 3. So that means we are guaranteed that every value will exist between 3 and 7. So we would say something like this. Since g is continuous, then the IVT guarantees the existence of all values between 3 and 7. And then we say the value 5 falls within this range. Is guaranteed because it's between 3 and 7. So somewhere there has to be a value of 5. Okay, it may even be lots of values of 5, but there has to be at least one that you can't avoid 5. Even if you tried, you could never avoid coming up to the value of 5. Okay, let's look at it again. Let k be a function divided by, now this is a piecewise function, so we have two parts. We have one linear function going to the left, and we have a different linear function going to the right. Must there exist some x between 0 and 2 for which k is equal to 4? So our interval is between 0 and 2, so we want to look at our endpoints. So our endpoints would be, what is k of 0? So when I plug k of 0 in, I'll be using this equation. So k of 0 equals 2. And the other endpoint is k of 2. And for k of 2, I'll be using this equation, which is going to give me 6. So I've got 2 and 6. So are we guaranteed that the value 4 must exist somewhere else? Okay, and then I'm going to say the answer. I hope you are coming to the conclusion. The answer is no. And the reason, even though 2 and 6 look like 4 is between there, like why doesn't that working? Is because we weren't told that this function is continuous. And if the function is not continuous, the IVT doesn't apply. So we better check the continuity of this function. So we're going to double check, well, shoot, I need to see what's going on to the left of 1. So what is the limit from 1 to the left? And that's 3. And then what's going on to the right of 1? And that is 5. So we've got a jump or a gap discontinuity going on here. So the gap discontinuity disallows the IVT. That means we're not allowed to use the IVT. So sometimes people fall into the trap of just jumping right into thinking, oh, sure, like 2 is less than 4, which is less than 6. It must be all great. And they say that the IVT does work. But unless you've established continuity first, it's not a viable option to use this theorem. All right, so that's it. Just a quick 13-minute review of continuity. And I hope that you don't have too much trouble with this assignment. All right, talk to you guys next time.